Hi, Laura. I didn't see anything yet. The class hasn't. There's 3 minutes before the class. So, can you hear me now? Good morning. Let me double check. Do you guys? Are you able to go to web work? Because yeah. Have you started with web work homework? Any issue logging in? Because you had that problem, so I was worried about other student having any problem logging into web work. Okay, so the beginning of semester, the important thing is being able to access the homework and being able to practice. So if you have any questions going onto the website, the WebWork website, you can find it on Georgia View inside content, and you go to overview. The second link, it's the WebWork link. If you've signed up for the class, I should have added you to the class list. But if you cannot log in, maybe you sign up later, or if I made a mistake, try to add it the class list. There's a class list editor. You can see it here, so I can add or change student information. If you have any issue, try to log into WebWork to do your work. Let me know so we can fix it, so you can have sufficient practice. And as we mentioned, that it's possible to attend class virtually, and each class session I posted a link for the class meeting. If you click on the class meeting link, it will the link will go to a app that's called Teams app. Your device, all computers have Teams app already, but if your device does not have Teams app already, you should install and open the Teams app. Each day before class, I'll log into Teams app on my side on the classroom computer. This is how I know that Teams app is already open. You can see activity, chat, Teams. There are some of the common functions of the Teams app. You can even use the Teams app as your phone because if you already have it, so use Wi-Fi as your calling services. So you can use this for calling people. So it has some function, nice function on the Teams app. Anyway, once your Teams app is open, you can attend class virtually. Today, Laura is in the online link. Laura, do you have any question with your web work? Are you able to open the web work link and do your homework online? Any question, any issues? Okay. So on the Teams app, when it opened, it looked like this, and then there's a camera. If you are okay opening your camera for me to see you, but most of the time I don't have my camera open. You can see that camera is flashed off, so I turn off the camera on the Teams app. The camera is right there in the webcam. But if I turn on the camera, it will start following whoever is talking in the room. I'd rather have the computer record the computer screen and record the calculation on the computer. So I did not turn on the camera, but I did have the mic turned on. If you want to talk during the class session, if you're attending online, then you have to have your mic open. And right now it is open on my side. That's why if you're attending online, you can hear me. If you cannot hear me when you're attending online, that's probably because I didn't turn on my mic there. And there's a mic on the computer. So there's two places I have to make sure it's open. I made tons of mistakes before. If I forget to turn that one on or turn that one on, then the recording will not be able to catch any sound. So it will be a silenced video. It happened before. So I recorded class sessions, didn't complain that I didn't know there's no sound. So nobody can know what I was talking about. So so if you attend online, you can find those functions. The places that you can change things around. This one is I'm sharing the entire computer screen. That's why the computer screen is being recorded during the class session. Essentially, that's how TeamNet works. Okay. As far as today, let me try to answer any of your questions. We have two homework already open. Let me try to log in from the student side. So this is what you should be able to see as a student, because you don't have those function that change the question or change the class list. So on your side, it looks like this. Right now, we have two sections already assigned. Have you had any questions? Where have you tried any of these? Any problem? Any hard questions? So we're doing okay with homework. Okay, so I'll move forward. I assume that you are doing fine with 1.1 and 1.3. So anyway, mention any question you had, or if you have any question that surprised you that we didn't talk about, try to bring that up. In the meantime, let me try to record today's attendance. We're using one of these questions that we practiced yesterday or the last week. All right, this is a limit calculation question. I'll let you do whatever you can do. Remember, to calculate a limit value or to determine the value of limit, you can have three methods. Number one, you can do it numerically. Try with number x approaching 10. Let's try to make x approaching 10. So x approaching 10 does not mean x equal to 10. It means x is taking on value that's closer and closer to 10. So you can definitely try with number. You try 10.1, 10.01, 10.001, or you can try 9.999. Those numbers will give you a rough value of this calculation. The true value are not being able to calculate it. You're determining it by seeing the tendency, not by calculating the numerical value. On the other hand, this is numerically calculated. The other method is graph. You graph the whole function. You're going to see where this is a curve. Actually, it's roughly a line, pretty much a line. You see where the line is going to on the graph. when x is 10, what was the y value on the graph? And that's determine the limit graphically. The third method is to determine the limit analytically. According to what we were talking about yesterday, you can factor the numerator and cancel the x minus 10. Then you can see the limit calculation become a completely different one, but they have the same limit. So you want to calculate the new limit because that one can be calculated by substitution. All right, I hope this makes sense. Let me try to record your response. I hope that you're able to follow what we were doing yesterday. And hopefully you can see this is similar to the last example we worked on yesterday. You can see it. Yes. Oh, that's not right though. But it's nice you limited it. But make sure you calculate it again. You might want to try a number to see the tendency. Like 10.01 squared minus 100, and find a number and divide it by 10.01 minus 10, which is 0.1. And once you do the calculation, you can see roughly how it is. It may not be accurate, but you're gonna be leading to one of those answers. So one of the ways is double check these numbers. Since we do have multiple methods, so it's beneficial to do all three if it's possible. I know graphs are not always available, but you can always do it numerically or do it analytically. Those two methods should provide you the same answer. If your answer is different when you try different solution, different method, that means there are errors in one of those methods that you try, because whichever method you try, they should give you the same answer. So this way you calculate something with two different methods and they give you the same answer. It's comforting to know that, hey, we're doing correctly because the two different methods are providing the same answer. That's right. Thank you. Oh, I forget to send you the link. Oh, all right. Let me give you the link so you can answer virtually online. Let me try to turn this on. So Laura, let me give you the personal Flickr link, and you should bookmark this because you can use it for anytime you're attending online. So open this page. Are you able to see it? Open that page and click on the answer that you think is the right answer. That way, in the system, it will be recorded. Okay. We're doing this calculation. With it, if x is approaching 10, what happened to x squared minus 100 divided by x minus 10? That's right. Thank you. No. No. You gotta start try a few number. I mean, if you try even 10.1 as x, you might be able to see a close enough number. I mean, not identical. Trying with a number that close to 10 certainly do not give you the exact answer, but give you the tendency, like what is it close to. It's called exploration with numbers. That's right. Thank you. The true answer, the best way to get the exact answer is to be able to calculate the limit analytically, analyzing the function, simplifying the function, determining the limit. That's right. You guys, okay, we're gonna have like have a way to handle it with a written solution. Sometimes we might know the right solution, but we can't explain it. It was okay for multiple choice question, but most of the time when you're doing work, you will need to explain or figure out a way to present your solution to make sure you learn how to write it down in process. Okay, let's see. I think I recorded everyone's answer. I'm trying to solve and see. The answer is 20. Any question? All right, you can certainly try numbers and the numerical answer. Oh, trying to, my phone is about to get out of power, go out of power, so I'll leave it there. So, but I'm gonna explain how to calculate it analytically, since that's the one that will give you the exact answer. If you try 10.01 or 9.99, it will be a rough answer, like approximate answer. But to figure out the answer without trying the number and calculate directly, we want to be able to simplify this limit calculation. What you can do is realize if you plug in 10, the denominator will be 0 because 10 minus 10 is 0. Numerator will also be 0. And 0 divided by 0 is what our textbook is calling this the indeterminate case, because we cannot determine by plugging number. If you plug in number, you can determine the true value. You have to try to determine a different approach. What happened here is we got 0 in the denominator, 0 in the numerator. So 0 is a factor in the denominator, 0, well, 10. 10 x minus 10 will be a factor in the numerator and the denominator. So the denominator is already factored. We'll try to factor the numerator. So as we try to go through, we aim to change the numerator in a way that made it possible for us to cancel a common factor. Okay. So numerator suppose it has x minus 10 because the denominator already has x minus 10. So we are hoping to rewrite the numerator in a way that they're equivalent, but we are changing it in the hope to simplify it. So what do we have if it's rewriting the x squared minus 100? What is that? X plus 10. So it turns out this got to be x plus 10. You can think of this as the square difference, 10 squared, x squared minus 10 squared is the difference between two squares. So this is called square difference formula. According to the square difference formula, that whenever you have a square minus b squared, like subtraction of 2 squared, it always equal to a minus b times a plus b. And because they're always equal to it, we treat this as a formula. So that's a way to factor this, right? One way to factor this is to realize and follow a formula in the process of calculation. Another way to think of it is that x squared minus 10, you can try this in second division. And we're dividing the x squared minus 100. So you go 1, 0, and negative 100. If you do consecutive division, you have to identify the coefficient. Degree 2 term, degree 1 term, there's no degree 1 term, so 0. Degree 0 term, if it's a number, it's degree 0, so it's degree 0 term. And we want to divide it by x minus 10, so the 0 in the denominator is 10, so we get a 10 there. And we drop down the 1, and we will multiply 10 and 1. When we multiply 10 and 1, this 10 and this 1, we will multiply them, we will be getting 10. 10 times 1, and then we add the 0 and 10, right? And then 10 times 10 is 100. And then we add these two, we add a negative 100 with positive 100, we have 0. So the 0 is a remainder, which means when the remainder is equal to 0, there's no remainder. That's when we have a factor. So what is a factor? Over here is x minus 10, over here is x plus 10. So the last row 1 and 10 indicate x plus 10 as a quotient. Over here, that 10 is indicating x minus 10 because if x equal to 10, x minus 10 would equal to 0. So these are the two that is a factor. So we write over here, those two are factors. So this is an illustrative example that consecutive division really helps when you want to factor a factor like that. So one way or the other, you can try the formula or you can try the division. Either way, we realize the numerator x squared minus 100 equal to multiplication of the 2 degree 1 term. And then we realize x minus 10 can be simplified. Simplify the x minus 10 will have a new limit calculation. So it'll be equal to limit of x plus 10, and x is approaching 10. So this process allows us to say that that the limit calculation are being transformed into a new limit calculation. Now we're able to, this is a simpler calculation, this is division. So the first one equal to the middle one, and then the one on the right is way simpler than the one on the left because of this process. So rewriting a hard question slowly into an easier question, and then with x equal to 10 in that process, 10 plus 10 equal to 20. So this actually finished the calculation. This will be an example where the limit is being calculated using an analytical method instead of numerical method or graphic method. Any question? Right, so the answer for this question will be 20. As you can see, the word analytically solving a problem is very broad, because being able to analytically solve something, that means you have to analyze the function. This function is a division between two polynomials. We go by analyzing it, by analyzing the polynomial into the fundamental factors or fundamental component. So if you have other function, you want to solve it analytically, that means you have to have some understanding on either how to dissect or decompose the question, or you have to know where those value is. So if you have limit of a logarithm, you have to understand logarithm. Limit of an exponential function, we have to understand exponential function. Limit of trig function, we gotta know what's the relation or what kind of formula is involved in the trig function. So it depends. That's why when you try to analytically solve a problem, you have to look at it case by case by practicing sufficient example. So I have to say, even for me, I can solve some problem analytically, but I cannot solve other question analytically. So it depends. And this is a broader sense, but we're just we're just training for those common questions that you often see in algebra or calculus. So for some of the really hard questions, people can write a paper for solving those problems analytically. So it's really, the level of difficulty is really wide. Some are super easy, some are really hard. And we can gain more skill by training, by practice enough. Okay. And this is pretty much 1.3 and 1.1. So today, if we're doing okay, since there's no question for 1.1 and 1.3, we're gonna go forward and talk about 1.2. Right. The title of 1.2 originally is supposed to be formal definition of a limit. Instead, we turn into Epsilon-Delta definition of a limit. The word epsilon is named for a Greek letter. The word delta also is a Greek letter. So why are we talking about these two Greek letters? Because we often use Greek letter to represent a quantity that often being mentioned in the argument. So if you ask why those Greek letters being mentioned, I think it goes back to the history of mathematics. When people who are invention of calculus theory, they are the one that were using those notation, and we're inherently start using them even in our definition of things. Okay, so let's start by a little bit. So we want to talk about formal definition, but we're going to try to look at our informal way of describing a limit. And you can see this is a couple of different ways. Really depending on book. Some books write it this way, some books write it another way. So when you talk about informal definition of limit, there's really a variety of ways of saying things. Here, given a function y equal to f of x and a value c, x value c, we see the limit of the function as x approach c is value L, right? How do we confirm that? So this is a formal way to say it. You can see if y tend to L as x tend to c. That's one. And two, if y approach L as x approach c. That's how I normally say it. I like to, the little right arrow thing I call approach. Number 3 is y is near L whenever x is near C. So that's another way to say it. You can see tends to, approaches, near. Those are words how we describe it, but they're really informal way to say it. How close is close? I mean, how near is near? So there has to be a quantified way instead of saying this informally. So this is why we're referring to a mathematical way to describing difference. How do you difference two number mathematically? You subtract them. For example, 6 and 8. What's the difference between 6 and 8? Well, 8 minus 6 is 2. So the difference between 6 and 8 is 2. What's the difference between 10 and 10.1? You take 10 minus 10.1, which is negative 0.1, but then you take absolute value. So the difference between 10 and 10.1 is 0.1. So often subtraction allows you to describe how close to number is. That's why we mentioned the subtraction here. So you can see a lot of subtraction in the limit definition. I guess I missed one page here. All right, so how do we formalize this? All right, the problem with this definition, I guess all my words, the discussion that were tend, the approach, near. So we want to find a way to describe them. So here is the 3 and 3 prime and 3 prime prime saying if x is within a certain tolerance level of C, then corresponding value y would be within a certain tolerance level of L. So meaning that if x is really, really close to C, closer than a certain amount, then y should be close to L, close to a certain amount. All right, another definition will be if x is within delta unit of C, then the corresponding value y will be within epsilon unit of L. And you can see those two notations. This one is delta. This is the Greek letter delta. I guess let me try to isolate that. And then this is the source of the definition or the reasoning, how we define the definition. Okay, so over here we're saying when we say this is how I write the definition for limit. We used to mention that when x is approaching C, the y is approaching L. That's when we see there's a limit. That's why we see y is the same thing as f of x. F of x is approaching L. That's our limit notation. So this is the same thing as saying limit of f of x when x approaching C is equal to L. Or another way to say that the limit of y when x is approaching C, limit of y is L. So you can see y and L, or f of x and L, is comparable. And then x and C is comparable because x is approaching C. X is getting closer and closer to the value C. So how do we describe the closeness? So we say when x is within delta unit of C. So when you see delta unit of C, this is a delta. That notation is spelled delta. It's kind of like a little triangle with a hook on top. This is how I write the delta, Greek letter delta. And so when we see x is within delta unit of C, how do you write mathematically? A number is within delta unit of another number. The notation will be when you see it's within that unit, means the difference between x and C when you subtract these two. I mean, x and C are really close. When you see x is close to C, x and C is really close. Close by how much? So close that the difference between them is less than delta. So we're pretty much using delta. Delta is supposed to be a positive number, a small positive number. We mean x and C are really close, and it's close, so close it's less than delta. Now, for example, if delta is 0.1, that means x and C is less than 0.1 difference, meaning if C is 10, x will be 10.1 or 10.01. X cannot be 10.3 because that will be too far from 10 if C is 10. So essentially the delta is providing a upper boundary for the difference that is forcing x and C to be really, really close since delta is taken as a small number. Are we okay? Okay, same thing over here. If you're choosing an x very, very close to C, then the result will be like see if or when x minus c is less than delta, then as a consequence, since f of x is approaching to L, then the difference between fx and L, fx minus L, that means the f of x is a number, L is a number, and since f of x is approaching L, so f of x is almost L, that means f of x minus L is a really, really small number, and we want to describe the smallness of it, like how so small that they're gonna be less than epsilon. So this is like a backward number 3. So you write 3 this way, but you write epsilon this way. So to me, that's how you write epsilon. This is a lowercase number in the Greek alphabet. How you write epsilon? I think is the letter E. Like it's corresponding to the E in the Greek alphabet. So anyway. F of x minus L is less than epsilon, meaning that f of x is really, really close to L. So this is our mathematical way to say if x is really, really close to C, then f of x will be really, really close to L. Okay, that's really how we describe the closeness, and this is the way we try to quantify the relation between x is the input value, f of x is the output value. So this process or this definition is saying, suppose the input value is really close to C, then the output value is really close to L. That's how we can tell that the function have a limit, and that limit value is at L. Any question? So we included or involved this 2 Greek letter as a number. So that's a small number. That also supposed to be a really small number. Only when the difference is small, that they're close. So you're supposed to choose small number for this and small number for that. And that's how we describe the limit exists if x approach C, f x approach L. It's really how we try to use a mathematical way to describe that they are close enough. Okay, so here is the official definition for the limit. It's saying that if you want x to be close to C, x have to be closer to C, and you have to allow that x can get really close to C, meaning that around the number C, you gotta have a little leeway for x to go close to. In the sense that suppose you have the number line, you will have to have on the number line, you will have number C, and you have to allow the x to go approach C either from the right or from the left. So you have to have a path for x to go to C. And if the function is now defined here or here, and then x cannot even get close to C, then we won't have a limit at all. So the number one thing is we have to have an interval. So let I to be open interval continuously. So why do we have to have that I have an interval including the C? Because we're trying to make it possible for x to go close to C, right? Right? If x is not even defined around C, or the function is undefined at places, if you don't see that interval, then x cannot get close to the C from left or right. So you gotta have an interval. So suppose I to be an open interval continuous C, then they give us a possible path to go close to C. F of x is a function defined on the interval I, except possibly at C. See, you can see that we don't worry about C. F function F, it's possible for a function F to be undefined at C, but you gotta be defined at anywhere else because you're gonna try to prove that there's a path leading to the limit. If there's no path, if there's no x approaching C, you have to make sure that x is possible to approach C. So x tends to C, and that has to be possible. That's why we need that interval. The function has to be well defined on the interval. Try to see the conceptual part of it. The underlying idea is the limit is really a process. We have to make sure the process happening. If the process is not happening or the function is undefined around C, well, the limit is not defined or there's no limit. Okay, we see a limit of fx as x approach C is L, denoted as a limit of fx equal to L. This is already talked about in section 1. If that means that this is the main definition part, means that given any epsilon, there exists a delta bigger than 0, such that for all x in L, whenever x minus c is less than delta, then f of x minus L is less than epsilon. So meaning that you can pick any positive number, and I can make f of x really, really close to L. So close, it's smaller than number. How do I make that happen? I can make x minus c close to c to a certain amount. So I can always pick a x value really close to c, such that fx minus L is really close to f. That epsilon is arbitrary. Given any epsilon, I can make it happen. That's how we know that limit f of x equal to L, because we can force f of x to be close to L to whatever. You can pick the distance, and whatever small number, I can make it happen as long as I can make x close to c, and that's the limit. That's proof that f of x is having an L as the limit. Any question? I hope it kind of makes sense. All right, so that's the logic behind it, and you can see this 2x value equality is the main thing. But together with it, we gotta see the process of how to make it happen. Once we determine that this is our definition for limit, since then, whenever you want to prove a mathematical formula limit equal to a certain number, you almost always go back to that logic. So in that process, we say you have to arbitrarily pick a epsilon, and you have to verify you're able to find a delta. So this is any epsilon, and this exists a delta. So you only need one delta, but this given any epsilon, meaning that any, so you can, it doesn't mean one single epsilon, you mean arbitrary epsilon. So we can choose a delta. So whenever x minus c is less than delta, f of x less than epsilon. So there. So then that delta is really dependent on the epsilon, because you are choosing epsilon first, and then you determine a delta, which gives you the level of accuracy between x and c that causes f of L to be close. And if you cannot make this happen, right? If you're able to find the x value, f of x minus L less than epsilon, and the limit equal to L, if no matter how you try, you are not able to find a delta to make this happen, that is just proof that the limit is not L. So there's proof to prove that limit of a formula equal to a certain number. There also proof that the limit is not a certain number. So sometimes we want to prove the limit equal to a certain thing, and sometimes we want to prove the limit does not exist, or the limit does not equal to a number. So proving limit is very important in mathematical proof. We have a class focused on making or writing mathematical proof for a lot of things in mathematical history. In this class, we just want to have some understanding of it. All right, so let's try an example. Okay, so this is a question about proving that the limit of root of x equal to 2 whenever x is approaching 4. You can see we are able to calculate the limit now. You can see if we plug in 4 for x, then root of 4 equal to 2. So there's no problem knowing that limit of root of x equal to 2 whenever x approach 4. But the thing is, we have this special where we're not calculating it, which the answer is already there, but we're trying to prove it. We're trying to show that limit of root of x is 2 whenever x is approaching 4. So how do we exactly show that? Over here, you're going to see this process. So we're saying you draw the root of x function, all right, and then we're going to find the number 4 right here. If you find the 4 and you go up to the blue curve, and you're going to see that the limit is 2. But according to the mathematical proof, we're not proving this, we're proving the tendency. So we can't directly make x equal to 4. We're making x like somewhere around 4, like somewhere here. If x is close to 4, you see, then the y value is close to 2. So we want to be able to model that closeness. So what do we see? According to our definition, we're saying choose any epsilon, I can make f of x and L closer than epsilon. So hypothetically speaking, we're going to try epsilon. Let's say epsilon is 0.5. So that will be the epsilon you see, fx minus L less than epsilon. Is it given any epsilon? Since it's supposed to be true for any epsilon, we're proving that if epsilon is 0.5, it should work. If epsilon is 0.2, it should work. If epsilon is 0.1, it should also work. We should also be able to determine the delta. So we're going to try to search for the delta by giving any epsilon. So you can see the entire proof focus on one thing. Take an arbitrary of epsilon, find the corresponding delta. So determine is, you see in the definition, we say given any epsilon, there exists delta. How do we know if there exists? You have to find it. So for any epsilon, finding the delta will be a key point in the proof of the whole process. So here we're giving it epsilon. Suppose epsilon is 0.5. So let's prove we can find that delta. And you can see the process will be, let me try to write it down and try to explain the process. The solution is already here. I just want to explain the process behind it. How do we prove this limit using a number? And we're supposed to prove it for epsilon, any epsilon, not just this epsilon. This was just an example to explain the logic. So suppose epsilon is 0.5, then we're trying to say we can make a root of x, which is, we see a root of x is close to 2. So root of x minus 2 is really close, so close that it's less than 0.5. Trying to make this happen. So how do we make this happen? If you want that to be true, you have to pick appropriate x value. So how do you choose a possible x value? And the process, we're going to make the x value close to 4, then a certain delta. So our ultimate goal, after a process, we're hoping to find that x minus 4. So we're trying to make x close to 4. We're trying to make x and 4 close enough, then a certain number. Then x minus 4 got to be less than something. So that's our goal. So the proof of a limit value is, if you want to write a proof, then you start with your target and you go for the beginning. So in the writing the definition, you actually start with here and arrive at here. Just go back to the definition that we see. See, according to the definition, you start with epsilon, take a delta, when x minus c less than delta, f of x minus L less than epsilon. So f of x minus L equal less than epsilon is a target, is a goal. But when you see there exists delta, is not so natural. It's natural when you read the definition, but when you want to guarantee there is this delta, you as a proofer, as people writing the proof, they have to show that delta truly exists. And that's why that given, which is the beginning, given any arbitrary epsilon, searching for the delta is the process of the mathematical proof. We're going to go back to try to explain how do we go from here to here. So the process really is in try to unwrap the whole inequality. And what you see here is how do we decompose the entire inequality. That is, we're trying to get x by itself. And then once the x is by itself, we minus 4, and then we will find the appropriate boundary for x minus 4. So we're going to start from here, and the whole process feels like it's solving an inequality. I hope that's kind of similar to what you learned in algebra. So what we're going to do, number 1, you see x minus 2 is less than 0.5. Number 1 is unwrapping the absolute value set. Essentially, we're removing absolute value sign, removing the minus 2, and remove the root of x to get x by itself. Once x by itself, then we minus 4, and we're getting close to the final goal. So keep in mind where do you start and where do you land it eventually, allow you to say what are we trying to do with that. So let's try to get x by itself. Number 1 is to understand how do we remove absolute value set. Whenever you have an absolute value of something, like absolute value of a is less than, let me see what number, let's say less than a. Okay, so if you have absolute value of something less than the positive number, how do we unwrap the absolute value? Easy process is to look at a number line. So there's a number line. Let's say x value less than 5. What does it mean? You can say that means x will be less than 5 and bigger than negative 5. For absolute value of any number, well, let's say 0, to be less than 5, meaning your right boundary will be 5, your left boundary will be negative 5. So right between the positive and negative value is where the true value is. So if absolute value of x less than a, to remove the absolute value, the process will be a will be less than a, capital A, and bigger than negative a. So this is how we can remove the absolute value notation. All right, going back here, we have root of absolute value of root of x minus 2, absolute value less than 0.5. To remove the absolute value, you will be adding a boundary. So we will have root of x minus 2 less than 0.5 and bigger than negative 0. So this will be the first step, and we would achieve one thing in the requirement of limit definition. We have absolute value because that's how you identify the difference between two numbers, and we remove the absolute value, and the whole process is ultimately try to find proper boundary for x. So we remove the absolute value. Now the next thing is to remove the minus 2. To remove the minus 2, we do plus 2. So we're gonna add a 2 for the middle because we're hoping to get the 2. Remove the minus 2 with plus 2. So we're gonna plus 2 on all three. Plus 2 the left, on the right, and in the middle. Then all three, and that the inequality separate the middle, left, and right. And that way we are able to remove the minus 2 with a plus 2. And we have root of x less than 2.5 and bigger than 1.5. You see the same thing in this process. If you're able to understand everything here, maybe you don't have to rewrite everything. I rewrite everything just to explain the process. Once we have root of x by itself in the middle, what we're going to do is to get x by itself, so we square. Square will remove the absolute value, will remove the root sign. So square the square root of x, we get x. I'm going to square this side. 2.5 squared is going to be 6.25. We square all three. If you square the 1.5, you're going to get 2.25. So this is the process to square all three terms. This is a composite inequality. That's why we have three sides. But the lucky part is there's only one x. So we focus on getting the middle x by itself. Now we've done that. Once the middle one is by itself, and we can try to arrive at what we want it to be. We want to have x minus 4, a proper boundary for x minus 4. So what we're going to do is we're going to minus 4 on all three. So we're going to do minus 4. Because ultimately we need to find out what is the difference between x and 4. We want to get x to be close to 4. So we're going to minus 4 all three. And once we've done that, we have this boundary that goes x minus 4 is less than, that's 2.25. This is negative 1.15. Negative 1.25. So we realize that now we have a boundary for x minus 4. So x minus 4 is going to be less than, right? Over here is the boundary for x minus 4 without the x value. This is 2.25. This is negative 1.75. Right, once you take absolute value, it's time to choose your boundary. The 6.25 minus 4 is 2.25. Then 2.25 minus 4 is negative 1.75. Among the boundary, we're choosing the upper limit. If we have to pick a small one. So 1.775 is smaller than 2.25, so we're going to pick 1.75, and that's why eventually you get 1.75. All right, and now we're done. That's essentially the delta. Remember, we are, we have epsilon identified as 0.5. We're choosing the delta. Right now, if epsilon is 0.5, we decided the delta, which is x minus 4's boundary, is going to be 1.75. So this entire process explains how we find it. How do we find that delta? When you say choose any epsilon, there is delta. Now it exists because you're able to identify the delta. So we are manually verifying that they do exist. The delta does exist. Okay. This is only example. The actual proof, you gotta prove for arbitrary epsilon. You can't prove it for 0.5. 0.5 is just example. This process explains the mathematical process. So here, how do we do it over here? This is the mathematical proof, and you can see it's about the same thing repeated with arbitrary value. So we're saying that root of x, y is root of x minus 2 is less than epsilon. So if this epsilon is any epsilon, any number at all, we're gonna try to find the appropriate delta. So you see the process again. Number one, root of x minus 2 is less than epsilon, bigger than negative epsilon. So that is a positive number, so that's positive root and negative root. So negative epsilon and positive root epsilon is going to be the left endpoint and the right endpoint of your middle term. And we add 2, and we square all three. So that was 2.5 squared before. Now it's 2 plus epsilon squared. Here we have 2 minus epsilon squared. And now we have, this is going to be that 2 plus epsilon. You have to square the entire thing. There's a calculation explaining 2 plus epsilon times 2 plus epsilon. 2 times 2 is 4. And there's 4 epsilon. There's epsilon squared. So that's the expansion on all of them. The reason we want to expand it because we want to get x minus 4. So we take x minus 4. So that take away that 4 and that 4. So yeah, you see those boundary. And then lastly, what do? We have x minus 4 bounded between this upper boundary and this lower boundary. But we're not trying to find x minus 4 boundary. We're trying to find the boundary for x minus 4 x value. So what's the x value for x minus 4? You can see this is the upper boundary and the lower boundary. We don't know which one is the true boundary for x value of x minus 4, which choose the small one. So we would say whichever is smaller between the 4 epsilon plus epsilon squared and the opposite of that one, the 4 epsilon minus epsilon squared. So we don't know which one is bigger, which one is smaller, because we haven't really calculated. The epsilon is arbitrary. So it could be this one bigger, it could be this one bigger. You never know until you actually pick the epsilon. Right now, because epsilon is arbitrary, so delta is in a sense also arbitrary. We don't know what delta is, but we got a formula for its computation. Any question? Are we okay? I feel like there's a lot of writing. It's already well written in the book, so I decided to just leave it. This process is pretty much the same process as here, except this one we use the actual number for epsilon. The epsilon is 0.5. This one we have the arbitrary epsilon. That's why the process had the epsilon carry together with it. This is a epsilon delta definition for a limit, and another example. We can see many of these examples. After see the limit calculation, the mathematical proof for the limit calculation, it can differ from one person to another person for the same proof. Like, see if you're trying to prove the limit of x squared equal to 4 is limit of x squared equal to 4 when x approaching 2. Even for that, we tend to have a different version of the proof. You can prove the same thing use one way or the other. Even if everybody is following the Epsilon-Delta definition, we may still have a different way to approach it. This is the proof that's given by the text. When you're trying to look at it, it looks messy because the way we treated many of the inequality and I call that inequality. It's just less than epsilon and less than delta. whenever you have an equality like that, you have to relax. Like this one, less than by a certain number, less than by how much? It depends on how you can be less than a 0.1 or 0.5, depending on how you treat the equality. That's why there's a different variety of methods. Now, this proof, you always kind of like the process, you always say, we're trying to figure out the appropriate delta to make sure x squared minus 4 is less than epsilon. So these two are the main thing. You have this, you try to determine this. But how do we guarantee whenever that happen, this delta, you're gonna have a formula for the appropriate delta. And in this example, we're deriving, see, x squared minus 4 follow the subtraction of squares. So we are able to write x squared minus 4 into the multiplication of the two. And that's where you have like factor this, and then you have this relation. This relation allows you to rewrite the left side of the equation, and then we have that one. So we have this idea that if you want to find the boundary for x minus 2, maybe this is a related boundary here. But in this boundary, there's a slight problem for x plus 4, the x plus 2. So now we have to relax our requirement on the x. We study what could be the lower boundary for the x plus 4. That's why we started to thinking about x plus 4's boundary. The rest is try to derive a way to handle the x plus 2. So that's the logic behind it. I would try to solve this problem in a very different way though. This is applying that formula. So sometimes you apply this formula, sometimes you can apply other ways to treat this question. Right. As far as this one, I would prefer to try to solve the problem slightly differently. For example, we can try just approach it algebraically. For example, if we are proving this, essentially we're saying for any, let me write the definition for limit again. So basically, if we are trying to right, if we're to prove this, we're trying to prove that for any epsilon positive, and we can find where there exists. In this case, really we are finding ourselves. Even though we say there exists, how do we know it exists? We gotta find it. So we can find delta, a positive delta bigger than 0, such that whenever x minus 2 is less than the delta, we will say that x squared will be x squared minus 4 will be less than epsilon. So this is the limit definition, and you can see the statement here. When you say we can find it, you gotta actually find it to finish your proof. You cannot just settle for I can find it, but you didn't find it and you didn't finish the proof. So that there exists the delta, or we can find the delta. That process determining the delta is the key idea of the mathematical proof. So what do? We start with x squared minus 4 less than delta, and that's how the textbook solution is, but the textbook solution went by a little bit more formula version of the solution. So we start with x squared minus 4 less than epsilon, right? Suppose for any epsilon, you got this inequality you want to achieve. You want to make this happen, and then we want to verify this is possible to make it happen whenever x minus 2 is small enough. So how do we do this? We can go by earlier discussion that you can simplify this by dissecting the absolute value. We remove the x value. The process of removing the x value, this you go x squared minus 4 will be less than positive epsilon and bigger than negative epsilon. So you can go through the same process of removing the absolute value, and then you can add 4 for all of them. You can have x less than 4 plus epsilon and bigger than 4 minus epsilon. Any question? Are we okay? So there's, so after we've done that, well, there's x squared. Okay, and then you see we were trying to find out the process for x minus 2, right? We need a boundary for x minus 2. What do we do next? We have to get x by itself, right? What's the next step? What do we do next?
Square root.
Square root. So we're gonna square root all three, and I'm gonna find the boundary for x would be x is less than root of 4 plus epsilon. This one has no problem because epsilon is a positive number. Root of 4 plus epsilon definitely is possible. The other side might have a slight problem. That is, we gotta take square root of 4 minus epsilon. Right, there's this underlying understanding that it's possible to take square root of epsilon. So that means you have to have the epsilon less than 4, right? If epsilon is a larger number, see, epsilon is a positive number. If epsilon is 5, this one is a root of -1. That's why this process have a little bit glitch. So in order to make that happen, we want to guarantee that epsilon is less than 4. And this should be less than 4 because normally this is a difference between the two less. There's supposed to be a small positive number. So epsilon is supposed to be really, really small. So this is okay so far. Epsilon is, as long as we guarantee epsilon is less than 4. So that's the boundary for x value. And remember, our ultimate goal is to find the boundary for x minus 2. So now we're going to do is we minus 2 on all three. So we're going to have the middle one minus 2. And we'll have x minus 2. It's less than root of 4 plus epsilon minus 2, and it's bigger than root of 4 minus epsilon minus 2. So now we are finding the boundary for x minus 2. And remember, we eventually want to find the boundary for absolute value of x minus 2. Yes, right? Right? So now we have to put absolute value. Now the question will be, what should be the boundary for x minus 2 absolute value? Okay, so then we need to find this boundary. So you can take this one as boundary, or you can take this one. Absolute value of this one as boundary. I mean, this one might be negative. It is a negative because 4 minus epsilon is smaller than 2, right? 2 is root of 4, right? Root of 4, that's root of 4 minus epsilon. Small number minus big number, that's negative. So you're gonna have to switch it so to get absolute value because you need to find absolute value as boundary. So now that means that we gotta find a delta. What is this delta? So we see we can find that delta is equal to a smaller one between the two. Whatever to the root of 4 plus epsilon minus 2, and this 2, that will be 2 minus root of 4 minus epsilon. These are the two numbers. And that finished determining the delta. Once you determine the delta, we find the appropriate delta. Every logic can trace back. If that's true, this is true, this is true, this is true, and that is true. So the proof, mathematical proof is supposed to go, if you get that, I can find that, this is happening, therefore that's happening. But how do we guarantee this two are happening? The entire proof, all our calculation is a proof that is happening because they're all equivalent to each other. I hope that kind of makes sense. Are you okay? So this is the one I think it's a little bit easier to follow than the textbook solution. The textbook solution have a little bit of deviation in the middle because that process, and we end up deciding to factor it out, and then that's what happened to this. And we see this and this have a similarity. We see a chance to have this being our delta, but that one have a variable. You can't make a delta equal to x. Delta is related to epsilon for sure, but it shouldn't relate to the x. So we find a way to simplify that, and this is what happened there. The rest is really try to make this happen, try to make this happening, right? So it's a little bit different than a common proof that I was easier to understand. Okay, so that one is a root function. We have a root function, a square function. Then the next example is the exponential function. The fundamental logic is very similar, so I'm not going to copy this one, but you can see this is a solution that's already being written. I guess we could do that. The process is similar to earlier. Let me just start over. This is what's being provided in the text, but if you go about try to determine the process yourself, you can see it's still follow the same idea. Basically is randomly choose any for any epsilon. I guess it's easier to start typing in. So we say for any epsilon positive, there exists, or we can find, it's basically the same thing. There exists a delta, positive delta, right? Such that whenever the x minus 0 is close, x is close to 0, closer than delta, we have the difference between e to the x and 1. E to the x has the limit that equal to 1. E to the x minus 1 is less than epsilon. So this is pretty much the definition for the limit. All right, and then if you want to prove the limit of e to the x is 1, you got to prove this. So how can we prove this? The epsilon is any epsilon. There's nothing to prove. That's just arbitrarily choose epsilon. But then this statement said there exists a delta. You have to prove it does exist. So that's delta. Determining the appropriate delta is the key process on proving the limit. So we're going to go ahead and start saying how do we make this happen? So the process will be, let's make e to the x less than epsilon and simplify from there to get to the appropriate delta. Process will be, you get e to the x absolute value, e to the x minus 1, which is less than epsilon. And we're going to try to unwrap the whole thing. You know what do we do first? Take away the absolute value. Yes. So number one thing is with the absolute value in the way we cannot do mathematical change to the equation. So we remove the absolute value and go positive epsilon on the right, negative epsilon on the left, so that there's no more absolute value sign. And then we can treat all three equally, left, middle, and right. What we're going to do is we first going to add 1. Just so we can remove the minus 1, we will plus 1, and then plus 1 here, and then plus 1 there. So we add 1 on all three. After we add 1, we then have e to the x is less than epsilon plus 1 and less than 1 minus epsilon. So we have right boundary and left boundary for the e to the x. Remember how to get x by itself from here? You have e to the x. How to get x by itself? Now, square root. Opposite of exponential function is like, what's the inverse? Natural log, right? We take natural log. So logarithm and exponential function are inverse function. So when you want to cancel something, you use inverse function. So like earlier, we have subtraction, and addition are inverse function. Division and multiplication are inverse functions. If you have division, you would use multiplication to cancel it. Now, if you have exponential function, you would use logarithm to cancel it. So we would take a natural log on all three. So you're going to do ln this, ln this whole thing, and ln this whole thing. So we're going to take natural log of all three. So one thing you should remember that natural log of e to the x. Now, ln is inverse of exponential function. Base e logarithm is ln, and base exponential function is e. So they are inverse each other, so you cancel each other. So then this equal to x. So, okay, so once you take a natural log of e to the x, it's x. The middle one is just x. And we end up having x in the middle. The right side is natural log of epsilon plus 1. And that one is fine because you can take a natural log of any positive number. Epsilon is positive, 1 is positive, so that is perfectly fine. There's a slight problem over here. Natural log of 1 minus epsilon. You can only take logarithm of positive number, right? So if epsilon is bigger than 1, we have a problem because 1 minus epsilon will be negative. Natural log of negative number is undefined. So we have to guarantee one thing, that if the epsilon is less than 1. But most of the time when you try to prove a limit, you are trying to prove the limit value is close. So epsilon is supposed to be a super small number. To make epsilon smaller than 1, it should be okay. Are we okay? Making epsilon larger than the number will be violating the rule for limit calculation. Normally, making it small wouldn't be a problem. So anyway, we keep that in mind. When that is happening, and we do have a boundary, this boundary will be natural log of 1 minus epsilon. Okay. Any question? And then what do we do if epsilon is bigger than 1? Well, if epsilon is bigger than 1, then 1 minus epsilon is negative, and this side, we don't have to worry about it because e to the x will always be bigger than this, right? It will always be, if e to the x is positive, it will always be bigger than the negative number. So then this side will be the natural boundary. So if it's really bigger than 1, then there's no worry on that side. We don't even have to solve it. We only have to solve it if it's that's someone that side will be existing. So anyway, this is our left boundary and right boundary for the x value. The next thing is, ultimately we want to find x minus 0's absolute value. That's our delta. So to choose the delta, you have to take absolute value. So take the absolute value will be the last step. So we want to take absolute value of the middle term, right? And it's less than. Now we have two boundaries for this. You take absolute value of x is either this one or this one. So whichever is smaller, because you are trying to find an upper boundary. The only thing you worry for upper boundary is this upper boundary might be too big. That's why we choose a smaller one between the two. So we would say absolute value of x is smaller than minimum of ln natural log of epsilon plus 1 is 1. The other one will be, this might be a negative number. Let's choose absolute value of ln 1 minus epsilon. Sometimes that logarithm can be negative. Just try to preventing that. Okay. Natural log epsilon plus 1, logarithm 1 is 0. So logarithm of number bigger than 1, this is a guarantee, that's positive. Because absolute value of x is upper boundary supposed to be positive, but natural log of 1 minus epsilon is guaranteed to be negative. That's why I'm taking the absolute value of it. Just are we okay? If you don't want to take the absolute value, you're going to put a negative before it. Negative natural log of 1 minus epsilon will be okay for the upper boundary. But anyway, these two numbers, there's no guarantee which one's bigger, which one's smaller. That's why we have to take a minimum, like min, the min function, just so we were not picking, we're not choosing the wrong one. So that finished it. This is our choice of the delta. So we say there exists a delta. Now we find it. This is our delta. So once you find the delta, that it's done for the proof. Okay, so basically, if you are writing the paper, like proving this, the process will be for this. We can see, and then we have this. How do we say that? And here is how you determine the delta, and then the rest of the process will goes up. So then you can't now just do this part or only do that part. You very likely have to have both. Sometimes some people, when they write paper, they like to put this in the middle of the discussion, but I would prefer having it in the following, having the definition and explain when I see there exists, this is how I know it exists. So that will be proving the limit of e to the x equal to 1 whenever x is equal to 0. This can be done. You can see that e to the number 0, any number to the power 0 equal to 1. And that's our exponential function example on the limit computation. Essentially, this entire section 2, in this calculus sequence, we often focus on application of calculus more than proving the calculus definition. But I still think it's meaningful to know the Epsilon definition, because if you are in theoretical mathematics study, like your ultimate profession, it depends which path you're going. So if you're really on the path for a theoretical study in your graduate school, you're gonna see this a lot. So I hope that we have an early exposure to it. So eventually, I cannot guarantee which way I should be. Some people prefer applied math. Some people prefer pure math. This is a pure math. It has lots of logical thinking. See the word given any, the word any, the word if it exists, such as, which is the logical reasoning. Some people have a hard time digest the idea, and some people find that interesting. So I hope that this gives us enough exposure, and hoping the exercise for this section of your class. So look for 1.2, and again, mention any difficulty that you have. And we can also always do it together. If you find this hard, I guess practice some might make them more meaningful. That'll be it for today. Thank you. Have a good day. You too. Thank you. Bye.